Can the last person please close the door? Please sit down, everyone. Okay, so people coming in, but thank you for closing the door. Let's start. Welcome to the afternoon session. It is my pleasure to say hello and welcome Marylou Gabrié, if I pronounced that correctly, I hope.
That's perfect, yes.
Thanks. She did her PhD at the ENS in Paris and is now working at the Flatiron Institute and New York University. And she's telling us about statistical mechanics of learning. So please go ahead.
Thank you very much. And first of all, thank you very much for putting together this great school and also giving me the opportunity to tell you about this line of work that is arguably a bit adjacent to the rest of the lectures that were in the school, where we are going to use physics to understand things about learning theory. So maybe a question. So I don't see the room. Is there a way I can see the room? Because I think on previous days you had, yeah, okay.
Sorry for the
small,
skills.
so. Yeah, okay. I mean, if ever I can see raised hands, we'll see. Okay. Before starting, also what I wanted to mention is that I've put the PDF of the slides on my personal page. Maybe I can paste the link actually in the chat to everyone. So you will find the slides here. So among the latest news, there is a paragraph about the school and the slides PDF. So if some of you want to maybe have, I don't know, have tablets and want to annotate while I'm speaking, feel free to do it. So okay, so let's start. So why am I saying that this is a bit of an adjacent topic compared to what's been taught in this school? So if you think of the ways physics and machine learning are connected, of course, we are using machine learning to do physics. And it's been the case since the very beginning. You can think of even doing a linear regression as doing some kind of machine learning or any methods of data denoising. And of course, this connection has been strengthened and maybe has flourished with the recent developments of deep learning that really revolutionized what we are able to do with machine learning. And there are many sophisticated applications that, as you saw already in this call. So today, what I'm going to talk about is the reverse connection between physics and machine learning, namely how to use statistical physics to understand machine learning. And this is not a new line of work. It started with the very beginning of maybe neural networks in machine learning, which was in the 80s. And the idea is that we are going to use the statistical physics toolbox to study models of learning. And sometimes it has also been used to inspire and design new learning algorithms. So the idea is to use maybe the thermodynamic limits or simplifying models and maybe witness phase transitions and so on, as you will see. So as I said, this started in the 80s, but since the mid-2010s, I would say, with the revolution of deep learning, there has been a new wave of interest towards this line of work. So if we want to understand the successes of learning, which is the main aim of this line of work, relying on the literature of statistical physics, we have to take into account three components, which are the data, of course, on which we are going to perform learning. What does it look like? What is there? Maybe it's text, maybe it's images, maybe it's music, all the structures that we can find, and also the structure we will find in the tasks that we want to realize on those data. Are we trying to do a classification, a regression, or how hard is this task to fulfill? So there is the data with which we are going to match a model, right? So it can be a neural network, and we can be talking about the architecture of the neural network we would choose, or it can be using a kernel method, or it can be all of these choices that we have available to perform learning. And with this data and this math architecture, then we are going to choose an algorithm, right? So the algorithm can be about training the training objective that we are going to use. So maybe the loss function, I mean, any objective we might fix for ourselves. And even when we have the objective, we may still have some freedom in choosing the optimization methods that we are going to use to optimize this quantity. So really, we have to take into account the three components and the interaction between the three components to understand the successes of learning. And indeed, there are a lot of things to understand still about modern machine learning. So I took this example of a Google Learnet to fix the ideas of what modern machine learning can look like. And I'm sure in this call, there has already been loads and loads of examples of very sophisticated tricks. I mean, reinforcement learning, recurrent neural networks, I mean, all of this that are nowadays constituting modern machine learning. And of course, one of the biggest puzzles in making them work is how come we are able to find good solutions, good sets of parameters for those models that are giving us very, very non-convex loss landscapes, right? So here I have this picture that is, if you want, materializing what we could expect would be a non-convex loss landscapes with here 2 dimensions, but it could be, as for example, for this Google Learnet, 7 million of parameters. So we would expect that there would be many local minima. And somehow, even if we are using mainly local optimization methods, such as gradient descent, we are managing to find good sets of parameters that have good properties for the learning tasks we are interested in. So that's definitely one of the puzzles of modern machine learning. And the second one I mentioned is about generalization, and precisely in the overparameterized regime. So what am I talking about? So I'm talking about looking at what's the generalization error that our learning method is going to have. That is, how well we'll perform the learning methods on data we haven't seen during the training. So how much we are able to go beyond what we've seen, the data we've seen during the training. And looking at how this quantity is evolving as we are increasing the number of parameters or the flexibility, if you want, of the model that we are using for the learning. And at first, there is this first stage that I can call a classical regime, where we have few parameters. And as we are increasing the number of parameters, we are getting a better and better fit, but we are not fitting the noise that is in the data. So this is why we have a good generalization. Now, as we keep on increasing the number of parameters, we would expect some overfitting to take place, right? So that we would be, like in this example, fitting the noise in the data. And this is what we are seeing with this overfitting peak, where we are generalizing very poorly. However, as we increase the number of parameters, we enter in this so-called overparameterized regime, in which the generalization error is going to improve again. So, of course, the plot I'm showing you is just a sketch, and it's not true for all algorithms. It's not true in all settings, but it seems that it's something that we are seeing in a lot of applications we have, a lot of techniques, of usual techniques nowadays in modern machine learning that are going to use a lot of parameters, such as, for example, the deep neural networks. So again, we have, in order to make sense of all this, to take into account all the components that are going to enter this success of learning. So today, in my talk, I'm not really going to tell you about very sophisticated architecture. We are, as you understood, not going to talk about applications in chemistry or quantum physics. But what we are going to adopt is the physicist strategy, but not only is, which is to study simple solvable models. And maybe it's a good time to already tell you that please feel free to interrupt me at any point and ask questions whenever you'd like. This is really meant to be a lecture, and if we don't get to the end because we've discussed too much, then I'm maybe even happier. So, okay, as I was telling you, what we are going to do is not study anything very fancy, I mean, in terms of architecture compared to what you have been discussing over the past week, but what we are going to do is study simple, what I would call solvable models. So the first example I can think of is the perceptron. It's also historically the first example that was treated, is the perceptron. And the perceptron is the one neuron model. So I'm going to sketch it in the following way, where I have an input layer that has a certain dimension D. And I'm computing the dot product with a weight vector W that has the same dimension. And then I take the sign of this product to give me a scalar output Y. So this is really the simplest model. I'm sure many of you have already seen it. And what does it do? I'm sure most of you already know, but what it does is, let's say that we are in 2 dimensions with our X, that it's going to draw an hyperplane in the space. So here it's just going to be a line, and it's going to classify +1 or -1 on each side of this line. So if we have points in the space, they're gonna have the different labels given where they are with respect to this line. And effectively, what it's able to learn is only linearly separable data. Okay, so what's the first question that has been asked and answered about this learning model theoretically is, what is its capacity, or in other words, how many data points can it fit? So it turns out that actually with pretty mild assumptions, so if we only assume that the training data points, the X's, are in what we call general position, which is some kind of extension of linear independence, then we can compute the probability that a random labeling is linearly separable. So if we take the Y's that corresponds to those X's randomly -1 +1, then we can compute the probability that it's linearly separable, so that the perceptron will be able to do the job as a function of a parameter alpha. So that's what is going to control actually the difficulty of the task. And it corresponds to the ratio between the number of training points over the number of training parameters, right? So it's intuitive that it's what's complicated. If I have more training points and less parameters, I'm more in trouble than in the other case. So it's this ratio N over D. And if we look at what this function looks like for fixed values of N's, so as I'm going darker in blues, I'm going to larger and larger N with the value of the training point that is going to infinity, but with a fixed ratio with the value of inputs. So when we are in this infinitely dimensional limits, what we see actually is that we have a step function. So I will be so bold and call this phase transition in physics, which as we are seeing in statistical physics are indeed happening in this high dimensional limit, which we call the thermodynamic limit, right, in statistical physics. And we see this sharp transition that is going on. So this, and that's for a value of 2, of twice as many training points as you have parameters or input dimensions. And so this is a computation that was first done by Cover in 1965 with geometrical arguments, but actually that can be reloaded in a statistical physics framework. And that's where I'm going to introduce to you a bit the notions that are useful in this line of work and that will underlie all the examples I will discuss along the lecture. So again, we are in this question of how many training data we are going to be able to fit with this perceptron. And the way that it was formulated in terms of statistical physics computation was to compute the volume in weight space of the number of the volume in weight space of the weights that are going to satisfy all the constraints of the random labeling. So you have this delta function that is going to equal the label in the training data and the one that is predicted by the perceptron. So with each new data point, it's going to have new constraints for the weights. So we are going to have a shrinking, of course, volume as we are adding training data points. And namely, to find this phase transition, we are going to look for the set of parameters for which, in the set of settings for which we have at least one solution. So we have a volume that is strictly larger than 0. And going one step further, we can rephrase it as with using the Gaussian representation of this delta function, where we are going to rewrite it as an exponential of minus beta of the square difference between the two, and then take the temperature 0 limit. And now it starts very much to look like a statistical mechanics problems, where we have defined an effective energy function. And the volume that we are looking at is resembling the computation of a partition function that is at the core of the statistical mechanics literature. So, okay, so we want to compute this volume. Now, why is this hard? So I'm not in the audience, so I guess it's maybe a bit difficult to be asking questions, but I don't know if somebody has an idea.
Yes, answer.
I mean, if you have a few parameters already, like the space is really, really big, since you can have all real numbers and all parameters. And if you have like 1,000 parameters, that's like a super huge space. So you will have to do sampling or something like that if you want to compute the integral.
Exactly. Thank you very much. So indeed, one of the main reasons why it is hard is the same reason as any interesting computations of partition function is hard, is that it's quickly going to become high dimensional for interesting problems. And it's always difficult to perform those high dimensional integrals. And indeed, if we wanted to, and also there is something else you should note, which is that this energy function is depending on the training set, right? So morally, for now, each time we have a training set, we are going to compute a new volume. So of course, and to do it, we could use, as you were saying, Monte Carlo functions, but this is not really going to teach. I mean, in this case, we even know that the result we are looking for is very easy, and that we are looking for a ratio of 2 between the number of parameters and the number of training data points. So where's the trick? Well, precisely what we are going to resort to is disordered system physics, and in the way that it's applied to learning. So I don't know if a lot of you are introduced to those concepts, but I will assume that not, and just give you the key elements I think are necessary to get the idea behind those computations. So in disordered system physics, we have 2 types of random variables. Random variables that are about the state of the system. So you can think of a spin systems, and you have your spin variables that are describing the state of the systems. And then you have also disordered variables. In disordered system physics is most of the time disordered interactions or couplings that are going to be deciding of what's going on in between those spins. What do they want to do? Do they want to align? Do they want to anti-align? And of course, then the distribution of states is given by a Boltzmann weight with an energy function that is going to depend both on the state variable and on the value of the interactions. And we will want to compute the normalization, the partition function, to understand the physics. So maybe the most common example of disordered system is the spin glass, where we have a Neising-like. Does someone have questions? I'm hearing something. No. Okay. So where we have a Neising-like energy function, where the couplings are distributing normally, so they are random, with a certain variance, and they are independent from one another. And that's the Sherrington-Kirkpatrick model. So I'm sure you remember the ferromagnet, where we would have all the Jij that will have the same signs, and we will have all the spins that want to be in the same direction. Here we have random interactions between the spins, and we can have frustrations with some spins that want to be up, some spins that want to be down, and maybe not everybody is happy with, there is not one clear configuration that will minimize the energy. So, okay, so this is the disorder complex, sorry. So it turns out that it's actually possible to do asymptotic computations for which we will have concentrations on typical states. So if we are in a very large system, then if we look at the disorder average of the free energy, the log of the partition function, then we'll see that it concentrates on the typical values. So if you just if you do the average, you will see actually the same free energy that if you just drew from the distribution at random one configuration. So you have this concentration effect, and ultimately it means that it doesn't depend on the realization of the disorder, and this is the simplification we are going to be looking into in our computations. And the way of computing this disorder average in this asymptotic limit is going to be through methods that I will not really enter into the details of today, but that I should name as, importantly, the replica computation, or variational mean field methods, or high temperature expansions. That's, I mean, I've been introduced in physics since maybe the 70s, and that now have an accompanying literature in mathematics, where the non-rigorous computations in physics are made rigorous by mathematicians, I mean, more and more, and since maybe Talagrand in 2006. So now, how do we use this disordered system physics to study learning problems? As it's been done since the 80s and 90s by, I mean, many people. We take the state of the system variable to be the learning parameters. This is what are our free variables. And actually, we are playing the role of the disorder, typically the data, that are constraining indeed the parameters to learn. And we are going to be able to average over the distribution of data to simplify our problem. So this is the typical mapping we have in between the two. If we go back to our problem of computing the capacity of the perceptron with this statistical physics framework, what do we have? So I remind you that we are looking at it by trying to compute the volume of weights in this parameter space that are going to satisfy the labeling, which we encoded by an effective energy function. What are here the disordered variables? Anyone? So, I mean, as I was just saying, this is going to be here the learning data. So we are trying to compute something that looks like a partition function in the weight space. And we have an instance of a data set that we will want to average over. And we'll see, and for example, here we can have random, I'm trying to remember exactly what oh yeah, and we are going to precise it later on, which distribution we chose for the data and that we are averaging over. And again, for random labeling of those YKs. And so the asymptotic computation using the replica methods is again going to give us a result that will depend on the parameter alpha. So I'm fixing the scaling where the number n of training points and the number of parameters or the dimension of the open space are going to infinity together with a fixed ratio alpha. And indeed, we are going to be able to compute this V of alpha, this volume of alpha, that is the asymptotic value of the disorder average of this volume. And then if we fix the distribution of data or the disorder, so either taking Gaussian inputs or taking binary inputs with binary weights, then we are able to compute the critical value of alpha for which the volume is going to disappear, so be equal to 0. And we find again this alpha c is equal to 2 that cover hard computing with geometrical arguments for training data and general positions, which is satisfied with high probability if we take random Gaussian data. And also we find we can compute for a different distribution of inputs, binary and assuming binary weights, what would be as well the capacity of such a perceptron, and it's 0.83. Okay, so that was a pretty long introduction, but that was meant to give you a bit a first idea of what are the key components of those methods and what we are going to try to tackle today. And if I just sum it up in 3 points, I'd say that we want to take into account the 3 elements that are composing learning methods to understand its successes, which are both data, models, and algorithms. We are going to use the statistical mechanics of learning and focus on simple solvable models. So here we had
the question.
Yes.
Okay, so in the original paper of Gartner, the calculation was a little different because she was using normalized vector W to N, and then, okay, and then theta functions with some kappa parameter, somehow describing errors or whatever you wanted. Anyway, the result was 2 for the analog of the cover calculation, and then some dependence on kappa decaying with growing kappa. Is the reason for that is because you use the Gaussian representation of the delta function and not normalized W?
No, I mean, I mean, here I was just describing an example, and I'm not, no, I mean, either way is okay.
Because you have 0.83, I understood. It was flashed very quickly, but I didn't.
So it's for binary inputs, the 0.83, and binary weights. So it's a bit different.
Okay, thanks a lot.
So okay, so yes, so I was in the middle of this recap of the introduction, where we take into account the 3 elements to understand the successes of deep learning. And to do so, we are going to actually focus on simple models for which we are going to be able to have solvable settings, such as this perceptron example, and use as a help the methods developed for disordered systems with those disorder average that are asymptotically converging. And okay, the first example was this capacity of the perceptron. So the scope of today's lecture is going to discuss classical and recent literature from a rather higher viewpoints, to give you an idea of what can be studied in machine learning with these statistical mechanics methods. And I will try to cover 3 sections. The first one will be to introduce you to the teacher-student paradigm. Then to develop more about what are models of data structure that we can treat with those methods. And finally, also touch upon dynamics of learning. Okay, so let's dive in the first important topic, which is the teacher-student paradigm. So the teacher-student paradigm is a toy model to study generalization. And what it starts with is to have a data generative model. So we are going to construct data sets that are going to be synthetic and depend on a given distribution of input that is typically involving an input distribution. So you can think binary inputs, you can think standard normal inputs as I was just mentioning. And then you will have an input-output rule. And typically this can be, let's say, probabilistic or deterministic, but you could think of taking a perceptron as a teacher model. So you fix the value of the weights, W star, and this is the model that is going to give you the relationship between your inputs and your outputs. And maybe you can add on top of this model a ground truth parameter distribution, from which you are going to select the weights, and we'll see later why is this useful. And okay, once we have decided for what's the data generative model, which we are going to call the teacher, we can sample from its training data set. So we sample, let's say, independently n pairs of inputs, outputs from this model. And then we are going to ask ourselves, can we feed the data, of course? And also, can we recover the teacher role? So maybe can we go even beyond only fitting the training data and have something that will generalize if we have recovered the right teacher role? So what we need in order to fulfill this program is, of course, to choose a model and choose an algorithm to realize the program. And choosing the model will be exactly defining what's the student in this teacher student. And for example, you can choose a student model that is going to be learned that matches the teacher. So let's say we had agreed that the teacher was defining an input-output rule that corresponds to a perceptron, then we can choose the same for the student. And as a remark for now, if we choose a matching teacher and students, then we are in the, if you want, an optimal situation in order to perform the learning, because we start with the right assumption about what was the underlying rule in the training data. Okay, so we have our data, we have our model. Now we need an algorithm, and the learning strategy might be that we are going to minimize the loss, as it's often the case, a square loss, a logistic loss, that is going to compare, of course, the training data outputs with the one that are predicted by the student. Or we can also adopt a different viewpoints, which is not completely unrelated, depending on how we formulate things. But we can also think of the problem as here a Bayesian problem, where we are going to compute what is the posterior distribution, which is the probability of having the weights W that generated the data set that we are seeing. So given the students' distribution corresponding to the assumption of how X's and Y's are linked, and given some prior assumption on the weights of the students. So given the training data and a priori on the students, what information do we have about the students? So if you want, it's a information theoretic analysis of what's going on during the learning here. So, and when we are in this setting where teacher and student are matched, we can say that we are in the Bayes optimal regime, where we are going to be able to minimize, just to be a tiny bit more precise, we are going to be able to minimize the loss, the squared error we are going to do on the weights, thanks to, yeah, okay, let's say that depends on which estimator we are going to choose. So let's say that, okay, we call this scenario the Bayes optimal scenario, and we are going to be able to have statements about what's possible. Yes, please go on with your question.
Hi, sorry for the interruption. I just wanted to ask if my understanding is correct. So in the framework that you presented in the previous slide, so our task, I will assume, is to infer distribution of the input data, right? In a learning task, or not? No.
Depending on what you call the input data. So the learning task is the, yeah, maybe I should have been, thank you for the question. I should have been more clear. So here the learning task that I'm going to consider, I think throughout this presentation is maybe the simplest supervised learning task, where I have a pair of inputs, outputs, and I want to learn a rule that is going to be able to predict the outputs given the inputs.
Okay, so in this sense, then my question is more like, I don't know, maybe I'm getting it completely wrong, but this sounds to me like creating a sort of a toy model, because I mean, we learn our teacher model from a true input distribution. Ah, yeah, you're right. Sorry, I didn't read the title about that. But yeah, no, then the question really comes like, how could you apply this to a real scenario? Like, because training a teacher network and then training a student which is able to learn from the teacher, I don't see what could be a straightforward application of this framework. I don't know if the question is clear.
It's very clear. Thank you very much for the question. So here, my motivation is not to be designing useful algorithms for practice. My motivation is to understand why useful algorithms today are working. What are their inner workings? And in order to understand, I'm creating for myself a scenario in which I can control what's going on, and I can then make statements about what are the determinants of the success of the learning. So it's not at all about applications, and it's all about learning. Studying the learning in itself. And in order to do that, I need to set for me the stage with both choosing data, model, and algorithm. And it's going to be very hard for me to make any general statements of what's going on in the learning if I choose for data MNIST, Cypher, some of the famous toy models in image machine learning. So what I'm doing instead is that I'm defining a simple model of how the data was created, and I'm not going to look at it when I'm doing the learning. I'm only going to look at the training data. So I'm mimicking what's going on in real life in a controlled scenario, so that I will understand what's going on. Is that answering your question?
Yeah, perfect. That's much more clear. Thank you so much.
You're welcome. Thank you for your question. So indeed, when I'm this matched scenario, which is not something that will happen in real life, exactly as you were saying, and I would never know in real life what's going on. But here, when I'm in this imagined scenario where I can match a student and a teacher, then I can be in the base optimal scenario where I can have a statement about what's the, for example, optimal generalization error I can obtain. And assuming that I have a square loss, the generalization error is going to be, so the square difference between the actual teacher prediction of the label, so the actual label in the type of data I'm trying to learn compared to what the student is predicting for the label. And this is going to be averaged right over all the possible data. So that's just the definition of the generalization error. And then it's going to be Bayes optimal when I'm computing this average with respect to the posterior distribution on the weights, knowing the data. So if I'm considering all the information I have on the weights, given the data, then I can compute this Bayes optimal generalization error. And we are going to be able, for example, in this case, I was just taking as an example where we have a perceptron teacher, a perceptron student, and Gaussian or binary inputs. Using the same tools I was just discussing of disorder average, thermodynamic limit, and replica computation, we are going to be able to compute the asymptotic disorder average generalization error. And it's going to be, again, a function of this parameter alpha that compares the number of training points and the number of training parameters. And if we take different distributions for the inputs and the weights, we can see different optimal generalization curves that I'm showing here for real data and sparse weight vectors. So not all of the entries are zero, but are non-zero, but they are real valued. And we see that as alpha is going to increase, so as we are getting more and more training points, we are going to be able to generalize better and better. And we can also see that if we have binary inputs and binary weights, then we are going to have at some point, so the generalization that is improving as we are getting more and more entering data points, and then we are going to have a jump to zero generalization. And that's what we would call again in statistical physics a first order phase transition, where we have this discontinuity to perfect recovery. And precisely what's going on when you have a zero generalization error in this matched training and student and teacher scenario, that the weights of the students are going to be equal to the weights of the teacher. So that's, if you want, what can go at best, given the information we have, given the size of the training sets all the time. And this is something that we were able to compute a number, if you want, we were able to compute statistically with the replica computation, which I did not detail. And I mean, if you are curious and we have time at the end, I can maybe show you a sketch, but it's pretty involved. So I'd rather not enter the details here. But what I didn't tell you about at all is what's a practical algorithm actually for finding those weights. So what's about practical algorithms? How do we train in practice? And how does it compare with this optimal possible generalization? Well, of course, one of the most popular algorithm is going to use gradient descent. And for example, if we are doing binary classification, we could use the logistic regression, gradient descent on logistic regression. And if we compare the performance of logistic regression, which are those blue squares corresponding to if we compare it with the base optimal solution in red, what we will see is that in the real valued case, it's somehow close to the base optimal, but not exactly matching the performance. And if we look at the binary case, we'll see that it's at the beginning not that far, but it completely misses the transition to the binary, to the perfect recovery. And of course, here we have binary weights, so logistic regression with a gradient descent is going to be indeed pretty bad because we need to project and so on. So it's somehow expected, but still we'll see that there would be enough information to have perfect generalization, and this is not achieved by gradient descent. Now there are another types of algorithms that I'm only going to mention and not really going to enter into the detail, but that are one of the other instruments of the statistical mechanics of learning that are message passing algorithms. And among them is belief propagation. So maybe I'm mentioning belief propagation because I'm thinking that maybe some of you have heard about it before. And it turns out that they are related, so to the mean field computation, so the replica computation in particular, I'm mentioning since the beginning of the lecture. And they are giving us on the plots the black dots. So for example, we see that in the real valued case, it's perfectly matching the optimal base solution. And we can see that in the binary case, so it's the black dot again. So at first it's perfectly matching. And then there is a region where it's actually not seeing that there is enough information to go to perfect generalization. And it's only going to have a transition a bit later and then find the perfect weights. What's also interesting about those algorithms is that their performance can be predicted with the same tools as I was mentioning. So if you look at the disorder average of their possible performance and you take an asymptotic limit, you will find, so here, for example, you have the green curve that is showing you what we call the state evolution that corresponds to the statistical prediction of the performance of the algorithm. So theoretically speaking, it's interesting to have an algorithm that you don't only need to run on specific problems, but that you can actually analyze and say, okay, given the parameters of the problem, I know that the algorithm is going to perform in such a way. And actually, for example, in this case of the perceptron, those message passing algorithms are also believed to be optimal among polynomial time algorithms. So what does this mean? This means that, of course, if there is a base optimal solution, then if we had an infinite amount of time to look for it, we would find it. And we would, therefore, it would be really what we would be aiming for. But we never have an infinite amount of time. And what we want is to have at most polynomial time algorithms, so that are taking a polynomial number of operations in the size of the system to be able to find the solution. And here we can see that, so the polynomial time algorithm of AMP with these black dots is already optimal. And here we see that there is this optimal algorithm that is unveiling what we call a computational gap. So we have this region of the parameter space. So again, this is the parameter alpha that is controlling the difficulty of the task. And we'll see that in this region, there would be enough information, but polynomial time algorithms are not able to discover it. And so we have this so-called hard phase that is discovered by those algorithms. So by no means those algorithms will be used in practice to perform training. They are a bit involved. They rely on some assumption. But here we can understand that there are some computational gaps that can arise if we are fixing our toy model of teacher and students to analyze it. Okay. So I'm not sure what would you like to do? Would you like to do only one break or two breaks during the overall lecture? Because I can either go on a bit and we can do a break a bit later, or we might also just take a break, a 5-minute break now.
Normally we have a 15-minute, one single 15-minute break, but you can.
Okay, one single break. Okay. So I'll continue a bit and we'll have a break a bit later. Okay, so here what I detailed was this first example of analyzing the teacher-student scenario, where we had a matched student and teacher that were these simplest of all neural networks of the perceptron. Now, what we can also do is a couple of others, simple two-layer architectures. And the first one that I want to mention are committee machines. So what are committee machines? They are two-layer neural networks where we are going to have, for example, 2 sign activations. But we are going, as we are going to see, we are going to have a lot of inputs and maybe only a few hidden units. And I will be more precise about it. And maybe we are also going to learn only the first layer. So from this teacher committee machine, we can, again, decide also for a distribution of inputs and so draw training data. And then I have a student model that can be, for example, matched. So the same committee machines. And as I was saying, maybe we are actually going to learn only the first layer. So with the high dimensional scaling, where we are again going to have a parameter alpha that corresponds to the number of training points over the number of parameters. Well, not exactly. I mean, there should be a number k. Okay, but I mean, it's n over d, so it's more the number of, let me say it's actually the number of training points over the number of input dimension. That is going to be over the 1. So meaning both n and d will go to infinity together. But we are going to fix the number of hidden units to be equal to O of 1, meaning that although the number of inputs is going to grow to infinity, we are only going to have maybe 2, 3, 10 hidden units. And this is so a setting we can analyze, and using the same tools I've been mentioning, we can compute a base optimal generalization error that will be a function, of course, of k and of alpha. And if here we take k is equal to 2 and binary weights, we can see, for example, such a generalization curve, so as a function of alpha, that is again going to decrease as we are getting more and more training points. So the bigger is our training set, the easier it gets at generalization. And at some point, we will have a transition again to perfect generalization that, if you want, is quite common in binary weights settings. And again, for this community machine example, we can also look at the corresponding message passing algorithm, and it's going to be the black dot in terms of the generalization. And you can see that the generalization is again going to miss the perfect generalization transition, where the base optimal generalization is going to go to 0, and it's going to jump only a bit later to the perfect generalization. And actually, it's quite nice because we can understand what's going on here by looking at what's the relationship between the student's neuron and the teacher neuron. So here, what is this Q00 and Q01 that are plotted in blue and in orange? They are looking at the inner products between, so the vector, so we have only two binary, two hidden neurons. So we have these two corresponding overlaps between maybe the first weight of the teacher and the first weight vector of the student. So the weight vector that is attached to the first hidden neurons and the weight vector that is attached to the first hidden neurons in the teacher and the student. And the same way is the cross value. So the first weight in the teacher and the second weight. So you have the index 0 and the index 1 in the students. And what we can see is that at the jump where there would be enough information, so we have a different behavior. Before, actually, both of them were equivalent. We had the orange and the blue that were superposed. And so pretty much, let's say the students is acting as if it had only one hidden neurons. It just, both of them are behaving similarly. And then at some point, we have this so-called specialization transition, where one of the neurons will start to have a big overlap with the first hidden neuron of the teacher, and the other one will start to be orthogonal as he's actually trying to look for the other neuron from the teacher. So here we can see what's going on in the learning thanks to this teacher-student scenario, where we can analyze how the students is getting to the knowledge of the teacher. Are there any questions? Okay, so
Yes,
that was, yes?
Hold on.
I was wondering actually how much will all this result be affected if we change the sign function for the labels to, I don't know, something else? Like
yeah, so I mean, that's a good question. And so the fact that you have, for example, a transition to perfect generalization is is made possible by the fact that you have indeed binary, you are trying to predict binary inputs. So if you change the activation function, you can have, you can see this transition to perfect generalization that is going to disappear. But morally speaking, you will always have this specialization transition that is going on. And you can do those computations. So here it was done for the case where you have a sign and a sign, but you can do it for sigmoids, you can do it for ReLU, and you will have slightly different diagrams if you are looking at those different activation functions. But morally, at least the computation remains the same. And sometimes there are some indeed activation functions that are easier than others, because in the computations, you have some shortcuts you can take. Let's say if you have something maybe odd or even, or but morally speaking, it's not really changing.
Great, thank you.
So maybe, I mean, it's not about I should say really the results precisely that I'm showing, but it's more about the concepts of what we can get to, and maybe the type of transitions we can unveil with those methods, I would say. Because indeed, as your good question is very good question is highlighting, if we change a bit the setting, then the exact phenomenology will change a bit as well. Okay,
Thank you. So I don't see any more questions. Any more? No, not a single one. So you want to take a break now?
Not
Oh,
quite yet, if
you
I may. Just
okay,
finish
sorry. I
this
thought
part.
you
That would be
interrupted.
great.
Okay, go on. Sorry.
Yeah, sorry. I know that it's almost 4 p.m. In Warsaw, but if you give me 5 more minutes, I can finish this part and then we can take a more natural break in the progression of the lecture. Okay, so this was an example of a two-layer architecture that we are able to treat with those methods. Let me give you another example that are learning with random features model. That is also going to be an example where actually the teacher and the student we are going to look at are not matched. So they are not the same models. So the students that we are going to consider is this random feature model that is like a two-layer neural network. So we have a first product between the first weight matrix and the inputs, a nonlinearity, and then an output weight vector, and potentially another nonlinearity. But actually, the weight parameters that we are going to learn are only the second ones, and we are going to have fixed first weight matrices. So that can be, for example, with Gaussian IID entries. And the teacher that we are going to consider is going to be not the same in the same shape, but let's say we can consider a perceptron as the teacher that will give us either regression outputs, so real valued outputs, or some binary labels. So depending on what we are doing. Okay, so now if we want to treat this this model, there is no such thing as a Bayes optimal generalization error because we don't have a student and a teacher that are matched anymore. So instead, what we need to do is to decide for a training objective. So we are going to find the weights of the second layer that are going to minimize the loss, and maybe we are going to add some weight decay, so some L2 regularization on the weights, which is very common in machine learning. And in order to use all the tools that I've been discussing, what we are going to do is to have a Gibbs posterior formulation of the problem, where again, we are going to put in an effective energy, the loss that we are trying to minimize. And this effective energy can be interpreted as having the loss corresponding to a likelihood, so the probability of seeing the outputs when we have a given input. And if you want a prior distribution on the weights, that if we take L2 regularization will correspond to having a Gaussian form for the prior on the weights. So by doing so, we are back in the framework I was discussing, where we are trying eventually to compute something that is related to a partition function, or at least some quantity that is marginalized over the weights, and we are going to assume that the weights are distributed according to this effective posterior distribution. And if we want to have precisely the minimum, then we'll take just a zero temperature limit again to have the results we are interested in. Okay, so in order to treat this problem, we have an important intermediary result that was discovered, let's say, multiple times. And the idea is that if actually we have Gaussian inputs, so X is let's say, standard Gaussian, then if we take the following scaling, where we have the input dimension that is going to infinity, the number of what I will call for now random features, so the neurons in the hidden layer of the student model that are also going to infinity, and the size of the training set that is also going to infinity, so in the sense that they have a constant ratios, then the generalization error asymptotically is going to be simply given by the difference, so the square difference, where we are going to take the activations of the students and the teacher, so those f hat and f0, of two Gaussian fields, so nu and lambda, that morally speaking, you can think of them as being what's the dot product between a typical, the weight vector with the typical inputs and the inputs also of the output nonlinearity of the students. And so you only need to know what is what the theorem is saying is that those two fields are jointly Gaussian. And so to compute the generalization error, what you only need is to be able to compute the covariance of those Gaussian fields. And these covariance can be computing either using random matrix theory tools. There are some new papers that are managing to do that, or the replica methods from statistical physics. So if I just, so I don't know if there's a question, maybe? I thought I heard something, no? Okay, so if we take this model and we use these replica methods to compute the Gaussian covariance between the fields, we are going to be able to compute the generalization error. And for example, we can do it for a regression teacher, where actually the teacher is a linear perceptron with some level of noise. And for a small amount of noise, we will see something like this, where we have, again, the generalization error as a function this time of the number of random features, which is going to control the number of parameters for a small value of the regularization parameter, or a so-called optimal value, so the one that will give you the lowest possible generalization error. And what we can see is that we are witnessing this double descent I was mentioning at the very beginning of the talk, where as we are increasing the number of parameters, we are first going to do maybe a bit better, and then we are going to a fit. But as the number is becoming bigger and bigger, we are going to see an improvement in the generalization. And the two curves of two different colors corresponds to having two different strategies for choosing the random features, so either Gaussian projections or orthogonal projections. And so we have this double descent with small regularization, and if we choose an optimal regularization, we can cancel it. And that's true for regression data, but we can also do the same computations for classification teachers, where we are going to have y that is the sign of beta x, and we can, with a certain probability, and that is going to be minus the sign with another probability with the value of delta that will correspond to the level of noise. And if we look at the same results, but for classification, we will see that the double descent is only slightly appearing, and again, disappearing with optimal regularization. And so that's an example in which we have a mismatch teacher and students, and we can make the student over-parameterized and so see and observe the role of over-parameterization in learning problems. So just before we make the break, let me recap this first section about the teacher-student paradigm, where what we have seen is that indeed this teacher-students is a way of creating simple synthetic problem that we are going to be able to study. In the case where the teacher and the student are matched, then we are in the so-called Bayes optimal setting. And we have seen that this information theoretic limit is sometimes, so we are able to compute it with those methods, but they are not always achievable in a polynomial time, a reasonable time. And so we can unveil some computational gaps. And here the methods that the examples we treated were perceptrons and committee machines that were Twolayers. And then in the mismatch settings, we can observe double descent phenomenon. And this we have observed in a model where we had the perceptron teacher with random feature students. So that's it for the teacher-student paradigm. And do you have questions maybe before we take a break?
I have a question if no one else in the physical audience has it. I just wanted to ask you if you could maybe repeat why we observed the double descent phenomenon in the overparameterized model and not in the regression task and not in the classification.
So, I mean, I don't have a simple answer onto why. It's what we are seeing in practice is that in the case of regression, you will have the weights of the students that are going to diverge when you get to close to the
Critical alpha.
Yeah, when you get close to the critical alpha, when you are just having enough actually power to be able to fit the training data. And so what you are doing is that you are pushing yourself very far to fit the training data and fitting very well the noise. Whereas when you have more parameters, you are actually going to learn a solution that is smoother, especially when you have regularization. And this is why you are effectively choosing a solution that is going to be better for generalization.
Okay.
Now, it seems that if you are considering a regression problem, this is going to be more severe in terms of how much you will have to overshoot to match the training data compared to what you are going to do with the classification error.
Okay. All right. Yeah, that makes sense. Okay, thank you.
You're welcome. That was a great question. Thank you.
I also have a quick one. What is your definition of optimal regularization?
So the idea that you are looking for the value of this lambda that is among all possible values that will give you the smaller generalization error.
Okay.
That's the definition of the optimal regularization.
And why does it disappear now in this case? Do you have any intuition for that? Like, why does it?
I mean, so as I was mentioning, so the fact that you are seeing this overfitting peak is because the weights are going to overshoot in order to be able to fit the training data. But if you are maybe increasing the value of the regularization, so you are increasing the constraints you put on the norm of the weights, then you are going to, when you are minimizing this loss, you are not going to precisely fit the training data. And what you are going to do instead is to favor a solution that is going to have low norm and that will be better for generalization. So this is why you are able to, well, I mean, this is the intuition onto why you are able to find a good solution. But it's not, I mean, there are a lot of things onto why the value of the optimal regularization. I mean, this is, for now, this is heuristic. There is no clear understanding of what explains the value of the optimal regularization and so on and so forth. So, I mean, those are intuitions, but there is still a lot we need to understand.
Quick follow-up. So when you actually increase the regularization even more, does the nature of the curve stay the same? And does this kind of indicate that, I mean, at least in your intro slides, you said we see the double well in real life, right? So is it kind of like saying that we don't actually use normal, I mean, the right regularization? Of course, it's like neural networks versus what you're doing now, but still.
Yeah, so, I mean, in practice, if, maybe in practice, what you will not that often be plotting this curve of how well you are doing as a function of number of parameters. So, and if what you are going to do is you have one task and you are going to look for all the best hyperparameters in order to have the best possible generalization. So if you are just in your practice of learning, I would say that you're not really likely to be seeing the double descent because you will not be doing the right plot to see it. But what we are trying to understand still is that how come that if we are not careful about which level of regularization we are taking, then we are seeing some overshooting at some point I mean, I'm already kind of like giving you the answer, but at first we didn't understand that it was this problem of overshooting that would create this overfitting peak. Or maybe I should say that what's even more troubling is how come we are finding good solutions past this overfitting peak, and how come the generalization error is still decreasing. So I guess the point is not really in practice, how come do I see or don't see this peak, but more how come do I find good solutions when I'm here? And here it seems that it's a beginning of explanation is that indeed we are going to find solutions that have low norm. And this is because we have put a small level of regularization, or maybe it's because also gradient descent is looking for those small norm solutions, or I mean, this is something that we are only trying to, I mean, only starting to unveil really.
Okay, thanks.
Welcome.
Okay,
Something
I don't
else?
see more questions. No? Okay, then thanks a lot for the first talk part. No, wait. We normally we only clap like after the talk is finished. So normally we do a 15-minute break. Are you okay with that, Marylou? Or
yes, I mean, yes, and I mean, I'll do as much as I can of what's left, but if we don't get to the end, it's okay, I guess. I mean, as you prefer. I mean, I'm fine with doing whichever break you think is best.
okay, then let's do a 10 minutes break, and when someone is late, then we will extend it to 11 or 12 minutes. Okay.
Okay.
See you in a few minutes. Thanks.
Thank you.
Marylou, are you ready?
Yes.
Please continue.
Thanks everybody for coming back from the break. So for the remaining time, what I would like to tell you about is how we can go further into incorporating models of data structure and how, to which extent we can analyze some dynamics of learning. So let's see what we can cover, and maybe I'll pass over some of the examples in order to give you a hint of all of the different things. So far, when we're considering structure in the data, what we've been changing mainly is the structure between the inputs and the outputs. And pretty much what we've been doing is choosing teacher models that were neural networks, either a simple perceptron model or maybe a committee machine. Now, what we could do is also be interested in the structure within the inputs. And the structure within the inputs so far has been mainly completely random, so either binary random or random white noise. So pretty much looking like this if we were thinking about an images. And this is nice because it's simple to plug into computations. But really what we would like is to be able to treat structured data. So if we look like, for example, the images in CIFAR, one of the toy benchmark data sets in machine learning, because they have this degree of structure that must play a very important role in generalization as well. But of course, the issue is that it gets harder and harder to solve models that are more complicated and also maybe offers us less interpretability. So let me tell you about one and maybe even two examples where we are incorporating more structure than completely independent inputs in the model. So the first one I'm going to discuss is the example that I call the salient and weak feature model. So it's still pretty simple. We have the structure of the input that is still Gaussian, but this time we have a covariance that is still diagonal, but okay. Either we have the isotropic case, which we have been mentioning since the beginning, or we have the anisotropic case where, so sorry, it's still in French here, where it's the data is structured, and namely what we are going to have is, if you want, some blob of data that is more extended in a subset of directions. So let's say that we have a sigma x1 that is much bigger than a sigma x2, that is going to affect a fraction phi1 of all the dimension of the inputs that is maybe small. And then we have a large number of dimensions that have a smaller variance. And this salience for the one that have a large variance and weak feature model can then be plugged into a teacher-student scenario that is similar to the one we just discussed, where we have a teacher that is actually a perceptron. Here the weight vector is called beta, from which we're going to draw the training data given the input distribution I was just mentioning. So either case, either sometimes it's isotropic, either anisotropic, and we are going to compare those results. And we have the students, which is this random feature model with the output weights theta that are the ones that we are going to learn. And again, if we do a replica computations with the same story as the one I've been mentioning since the beginning, then we are able to compute a disorder average of the generalization error, so the expectation of the squared loss between the training data and the one that is predicted by the students, that is going to concentrate on a function that is going to depend on the ratio between the number of inputs and the number of training data points, the ratio between the number of random features, so the size of this vector, and the inputs as well, and the strengths of the salient feature, and also actually how the salient feature are going to be aligned with the teacher rules. So whether we have this teacher weight beta that is aligned with the dimension that will matter, that will be with the most variation in the inputs, or whether it won't be. So whether we have the more salient feature that are relevant for the task, or whether they are not. And if then we again look at how this generalization error that we computed theoretically is evolving as we are putting more and more flexibility, more and more parameters in the problem, we are going to see a gradient, a double descent, as we have just said. So this is the isotropic curve we have just seen before the break. And here in green, you also have the structured case, where we are going to see that actually the structured data, the structure in the data is detected, and we have a generalization that is improving before the overfitting peak. Because effectively, actually, the dimension of the problem is smaller because we have everything that is concentrating on the salient feature. And then we have also, after the overfitting peak, a generalization error that is much better than if we don't have any structure. And in a sense, we can say that the double descent is here exasperated by the structure in the data, when indeed the teacher is going to be aligned with what are the salient feature in the problem. And just as we are seeing this, I can mention also here something that I haven't thought of saying on the curves before, but that we were already seeing, that the solid curves that correspond to the theory, so the asymptotic calculations I'm discussing, is actually matching closely what you would say on random instances of the teacher-student problem for, let's say, a fixed dimension that is equal to 100. So really, you have these concentration effects that makes it that you can predict what's going on already at moderately large size by the asymptotic computation at an infinitely large problem. So, okay, that's the first constatation of what's going on if we have structure in the data. And we can also push further and, for example, look at the interplay between the data structure and the loss function. So again, we are on this diagram trying to here look at the interaction between the algorithm and the data in explaining the good generalization properties that we are reaching while learning with this model. And still with the same teacher-student scenario, with the student of random feature, we can vary the loss that we are using in our training objective. And we can see, for example, for a squared loss and a logistic loss, different curves that we are going to see with all things equal, besides just changing the loss. And what we are going to compare are the different scenarios, whether the data is isotropic. So this is what we were seeing, that actually we have a small, with the square loss, this is what we were discussing before, we have only a small overfitting peak for this classification problem. And when we have the logistic loss, we have this almost vanishing, we almost don't even see this double descent in the asymptotic case. And we can see that with the aligned structure of the training inputs with the target tasks to fulfill, we have an exasperated double descent. But in the case of the logistic loss, we are just going to see an improvement of the generalization, sorry, and okay, again, no overfitting peak. What else we can also see from those curves is that the logistic loss seems to be taking most advantage, and more advantage of the structure, as when it's structured, it has a better improvements in the generalization than for the square loss. So this gap is larger than this gap. And this is something we can again investigate further because we have those toy models that we are using to make our computations. So we can tweak them to try to see what we are trying to understand. And here, for example, on this plot, what we are varying is precisely this teacher data alignment. So if you want, I have this blob of more salient features and this teacher vector beta that is going to rotate so that it's more or less aligned with what's relevant in the data. And what you can see is that if you have, so we have compared here noiseless and noisy arguments, but each time that we are going to go from square to logistic, we are going to have a gap that is opening as the data is more and more aligned with the teacher. And interestingly, it's also something that we can see on real data. If we are computing a PCA, so principal component analysis of some of the same simple famous data sets of image machine learning for benchmark, MNIST and CIFAR. And we are rescaling the different components so that the data is more or less aligned with the salient features that are useful for the learning. And we can see here as well that as we are increasing this alignment, we are going to have an opening gap between the logistic and the square. So this is an example where simple solvable models will help intuition that are further confirmed on real data experiments. And that was also the first example I had for more structured model of data, which was this fairly simple, weak and salient model where we can control how data aligns with the task at hand. Now we can do even better. And towards more and more realistic data, we can even use trained generative models in those computations. So let me just give you the idea, and we're not going to really enter into the details. But the idea is that instead of having just a teacher that is maybe a perceptron with random Gaussian weights, or that is Gaussian inputs that are Gaussian distributed with some specific variance, we are going to take much more sophisticated inputs that will have been generated by maybe a deep generator, such as a generative adversarial network, a GAN, or a VAE, or we are able to pre-train this generator and consider all of this as the input distribution. So having just the data that is just generated. So let's say that now we are learning on data that looks like not a Gaussian blob, but that looks like a manifold of images of dogs. And then putting a synthetic teacher on it, we are able to learn on either directly those inputs or some feature maps that can be random, like in the random feature model, or that can be learned. We are able to analyze the learning of a student on this data. So here, the Gaussian equivalence principle that I mentioned is crucial. And what's actually going into the computation is that we will need to estimate what are the covariance that we use to compute analytically. But once we have estimated them, for example, by Monte Carlo, we are able to characterize the learning with the methods that I was mentioning. And for example, we can look at what it gives for predicting the performance of random feature learning on CIFAR. So here you have black and white images of CIFAR that are from the real data sets. Then you have black and white images that were generated, so after learning a generator on CIFAR, and that are actually the data that we are performing the analysis on. And we can see that if we compare the mean squared error that we are using in terms of the generalization mean squared error as a function of the size of the data set, the sampling complexity, then, and if we compare the theory that are the solid lines with the crosses that corresponds to actual numerical simulations, we can see that indeed the theory is still valid and able to predict those performances.
Can I ask a question?
Yes.
Sorry. Just a curiosity. So in this task, we again have a teacher network from which we generate our input data for our student network, right? But of course, this means that we have an intrinsic bias in generating our input, because of course, this relies on the fact that we have a well-trained generator that, irrespectively for how well-trained this is, it will always not be a perfect distribution of the input manifold. So now my question is, have you, or is there any work checking how the quality of the input that are used to train the student affects the way the student learns? Meaning that if I take a manifold of generated inputs and I add to this an increasingly amount of data coming from the true distribution, do you know how this influenced the learning of the student?
So, okay, so there's different things. So the students is only gonna learn the tasks that we are synthetically creating for it with this data that is coming from the generator and the corresponding teacher given labels. And you cannot put, in any case, actual real data into the analysis of the learning of the students. So if you want, if you would like, empirically, you could compare how well is a student, I mean, just by running the experiments, you could compare, okay, let's say that I train a generator on CIFAR, and then I try to make it learn the labels of CIFAR. I tried to make a student learn the labels of CIFAR, or I'm actually taking CIFAR and training the same network to predict the labels of CIFAR. Are there different performance? And that is something that can be done experimentally, but I don't think this paper has done it, which is this paper that did this comparison. And I don't know exactly how this would, I mean, I don't know the answer to this question, but that's definitely interesting. But what you can see in this paper that I think is related to your question and probably relevant to mention here is that there are actually some training regimes in which this correspondence will break. And this is, I mean, touching upon what you were mentioning of how close we are to the real world when doing those experiments. So maybe if you are interested, what I can recommend is reading more in detail this paper. And otherwise, maybe performing the experiments of that, I mean, the experiments we were just mentioning would be also interesting.
Okay, no, because as a quick follow-up, I'm thinking about this since out of distribution detection is a very crucial problem in the current machine learning developments. And I never worked with teacher-student frameworks, but I was thinking also in this direction, like if we can infer some knowledge of how this out of distribution detection might be improved by getting inspiration or by seeing how different outputs from different distribution affects the teacher student framework. But okay, this is just a naive thought that
yeah, no, I mean that's interesting. And okay, I'll think more carefully about whether there are works that I know of that are related more directly to this out of distribution detection problems. Okay, and thank you.
Thank you.
Okay, and with this was actually what I wanted to tell you about possible models of data structures that can be incorporated in the learning. And what we've seen is this salient and weak feature model that is pretty simple, but is already successful at giving us some intuition of the impact of data structures on generalization. And going further, it is possible to incorporate some synthetic model that are trained and that will mimic real data and that remain amenable to analysis, although it's not, as we were discussing, not exactly real data, and there are some conditions to this success. So do we have more questions maybe before I move on?
I don't see any questions.
Okay. So the last chunk of this talk would be about now getting into algorithms. So we've seen this teacher-student framework. We've seen how we can try to improve it with having more structured data, but we haven't really touched upon specifying which algorithm we are using to learn. We've used just Bayesian optimal performance or message passing algorithms, but none of them are very realistic. So what about stochastic gradient descent? So in which you have a loss, as you know, that is summing a given instance of a loss over the different inputs you have on your training sets, and then you are taking gradient updates on the parameters of your learning model in the opposite direction of the gradients of this loss, and you can do it on all the example at once, or you can do it by taking a subset of the example in the so-called stochastic gradient descent. So, of course, as you know, I mean, we can sketch this algorithm in the following way. We have an initialization, and we are searching locally for the optimum. And of course, this is meant to not be optimal if we have non-convex losses, or many things could possibly go wrong. So there's definitely a need to take into account the fact that this is the method we are using in order to understand really what's going on in modern machine learning practice. So that's, as I was saying, the last chunk of today's lecture, and we'll occupy the few minutes we have left. And what I should say is that as soon as the 19th, actually, there had been analysis of online learning in simple neural networks frameworks. So what's online learning or online gradient descent? We have a stream of data that are coming one after the other. And after receiving one input data, we are going to take a parameter update. So we are updating on the fly or online the parameters, one example at a time. And on top, we are going to assume that we see only each sample once. So the size of the data set we have seen is actually equal to the number of iterations we have taken in the descent. And the analysis principle then on if I give you of the perceptron example, so where we have a matched teacher and a student, let's say for this example, where again the teacher is going to send training data points one by one to the teacher. So let's say that we take a square loss. So for one sample, we are just going to take the square of the difference of what the teacher had predicted and the student is predicting. And then we have the parameter update that corresponds to taking the gradient of this loss and having, of course, a learning rate. And to treat how this is going to evolve and how the generalization is going to evolve, we are going to take a high dimensional limit and take a disorder average. But also on top of it here, we are going to take a continuous time limit. And doing all these steps is going to be made possible by precisely being in the online setting where we have actually uncorrelated samples that are arriving at each update. Since we are not looping over a data set, we are having this simplifying assumption that we are only seeing each data points once. And so if we go into more details of how this goes on in the online learning of the perceptron, what's going on is that we are going to follow the quality of training in terms of what we call overlaps. So the overlaps are going to be the dot products of the student's vector with itself. So at iteration k, so it's the norm of the vector of the students, if you want. And we have this cross overlap between the weight of the student and the weight of the teacher. So of course, we want them to have a high overlap. We want them to be collinear and of the same norm. So to maximize this, I mean, there are some constraint on their norm. So in the end, we want them to be, we want this overlap between the teacher and the student to be as large as possible, and eventually to have them equal. So again, we are going to take the continuous time limits and this high dimensional limit and the disorder average for our updates of parameters. And this will actually result in a set of closed equation on the overlaps. So we have a set of ODEs on the overlaps that are going to describe what's going on during the learning of the online learning of this perceptron problem. And again, the generalization error that corresponds to the expectation of the squared error over the whole data distribution is itself going to be able to be expressed as a function of those overlap R and Q, and will converge and we can compute it as in the continuous time limit as a function of time. And this was, for example, done by Bill and Schwartz in 1995 for the first time, where they actually looked at, for example, here, the different convergence rates that they got for different learning rates of the generalization error in a perceptron model. Okay, so that's the principle of how this dynamical analysis can be performed in the very simple example of the perceptron. Now we can go further and, for example, apply it to committee machines and have the online dynamics of committee machines that we were discussing earlier in this talk. And here we can even use committee machines and go beyond the case where they are matched, where we have the same committee machine for the student and the same for the teacher, sorry, and the same committee machine for the students. We can assume that we have maybe M hidden units in the teacher and K of them in the student, so possibly more or less. And again, the analysis of learning is going to require to define the overlaps. And this time, if we start by only learning the first layer in the student, the overlaps will look like matrices. So the overlap between the teacher and the student is going to be a matrix of size K times N, so size of the student, size of the teacher. And the self-overlap matrix is going to be K times K, so looking at the overlaps of the K different weight vector in the students. And again, we are going to be able to compute the generalization thanks to, when we know the value and the evolution of those R and Q. So there will be a set of ODEs as well that I didn't even write. And then we can look at what we get out of this type of analysis. And what we see is that here in the generalization error, as a function so of the time of the training or the size of the training sets, that we are going to have for matched teacher student in here for different value of K. So a value of the asymptotic generalization that is going to decrease as we increase the value of K. And also we are going to observe those plateaus that are then going to be escaped. And here we actually going to see again an instance of this specialization transition I was mentioning earlier, where at the plateau, actually, if you look at the matrix R that corresponds to the overlaps between the teacher hidden vectors and weight vectors connecting the inputs to the hidden units and the students, what you are going to see is that on the plateau, there isn't much overlap between any of the student vectors with any of the teacher. Whereas after the plateau, you have had this specialization transition, and you can see that the first of the student and the first of the teacher have a large overlap. The second and the second have a large overlap. And then between the teacher and the student, they exchange the fourth and the third. But clearly, the student has found that it's specialized to the 4 different weight vectors in the teacher. And this is what is giving this very good generalization rate. So you can really see this happening. So you can see in green the theory that is from integrating those ODEs, and in crosses actual instances of running this algorithm. So that's a really nice instance of again computing the dynamics with this mean field type of computations and these other averages, and where we can see the specialization transition. So now we can also go further and look at what's the role of overparameterization and feature learning. And so the idea of overparameterizing here will be to have a student that has more hidden units than the teacher. And interestingly, if we are only learning the first layer, what we found is that if we look again at those self-overlap matrices and the matrices of overlap between the student and the teacher, it's that there's only 2. So here we have a teacher with 2 neurons and a student with 5 neurons. And among the 5 neurons of the students, only 2 have significant norms, and the other ones are pretty much 0. While here we see indeed that the 2 neurons are found 2 neurons of the teacher. They have good overlaps with both neurons of the teacher, and then they have norm 0. And interestingly here in this setting, if we are only learning the first layer, then we are not helping the generalization by over-parameterizing, by adding more neurons. And this is here, we are adding neurons in the students compared to the teacher, and we can see that the scaling of the generalization error is increasing. And namely, it's because we are just picking up more noise by having more neurons, but we are not learning anything valuable by having it. Meanwhile, if we are actually learning both layers, what we are going to observe is that as we are increasing the number of students of hidden units, we are going to have a asymptotic in time generalization error that is going to be smaller and smaller. We still have the plateaus that we were mentioning. And if we look at the value of the overlaps, we will see that it's again the same case where we have 2 neurons in the teacher and 5 in the students. We'll see that we have several neurons in the students that are going to overlap with one given neuron in the teacher. And it's going to be, we have the 1, the 3, and the 4 that have overlapped with the first student neuron. Sorry, here we can see. And we're going to have the 1 and the 2 that have overlapped with the first teacher neuron. And effectively, actually, what they are doing is that they are joining forces and are going to average their power to try to grasp what was in the teacher. And in this case, it's called the denoising solution because you have multiple learners, if you want, for each of the hidden neurons of the teacher. We are going to see that over-parameterization will be beneficial, and we're going to have generalization error that decreases as we are increasing the size of the students. So that's again an example where we are able to study the dynamics of learning and see and understand in which case it's beneficial to over-parameterize. So in this simple model of mismatch committee machines. Now, I mean, there's only a few minutes left. So the only thing I wanted still to mention was whether we could go beyond this online gradient descent paradigm and whether we could analyze multipass stochastic gradient descent, where we have a fixed data set and we are going to reuse periodically different samples. So it's possible, but it's a bit more involved, and this is using dynamical mean field theory. And okay, I'm maybe not going to detail this example for the sake of time, but if you are interested, I recommend you to read this paper by Francesca Miniaco and collaborators, where they are dealing with perceptron classification on Gaussian mixture and able to look at the effect of batch size or the regularization. So in actual mini batch gradient descent setting. And okay, so just to recap what we have seen on this last learning dynamics of learning check of the talk, we've seen that especially in the online gradient descent setting, it's possible to, thanks to this disorder average and asymptotic thermodynamic limits, to look at the performance and characterize the performance of the algorithms in terms of a closed set of ODEs on overlap variables. That it allowed us in the committee machine to describe the onset of the specialization transition and understand the role also of over-parameterization. And what we didn't have time to cover is that the dynamical mean field theory can also, which is a bit more involved, can help study even batch gradient descents in simple models such as the Perceptron. So maybe I will actually conclude and then take questions for the sake of time. Just to go back on the broader view of what we were trying to do, and that is involving data, models, and algorithm assumptions into understanding what are the determinants of the success of deep learning. And we focused on simple solvable models. And what we should focus on I mean, going forward is trying to have more and more sophisticated models that are teaching us about what's going on in real life classifications, real life applications, and that's was precisely the topic of one of the last questions I got. So in terms of models of data, we want to try to approach this real world data and see whether we can understand what aspects of the structure are really helping, for example, generalization in over-parameterized regimes. In terms of architectures, we've talked about the Perceptron and some simple two-layer architecture. We are trying to move forward to having more, for example, deeper neural networks, which are the workhorses of many modern machine learning methods. And in algorithms, of course, we have also some tools for online gradient descent, but it would be interesting to move closer and closer to more correlated algorithms that are actually using some information about former gradients, such as Adam, and that are also key determinants of the successes of some trainings nowadays. And before I close up, I also wanted to mention that there is a broadening use of so-called mean field approximations in the deep learning literature beyond what I've been discussing, where we are basically taking advantages of concentration effects thanks to randomness in the large size limits, let's say, and that is covering many different fields. So I invite you to go over maybe those different applications if you are interested. And finally, I wanted to mention that I've added in the slides, so which are available on my webpage, and I don't know if they will also be made available on the website of the school, some selected references about that I believe are pedagogical about the topics I've mentioned. And with this, I would like to thank you very much for your attention and the nice questions, and of course, the organizers of the school. And I apologize for running a few minutes over. I'm happy to take questions.
Thanks a lot for your talk. It was very interesting. Who wants to ask any questions?
Hi. I'm wondering what the results on over parameterizations, like what implications do these results have on real neural networks? Because I was thinking one thing, so when we were in the case of learning just one layer, like all the additional weights were useless or even harmful, and they were going to zero. So I was thinking in a regime in which we have a single layer neural network, like a restricted Boltzmann machine or so, do you think this would happen or should happen?
So I'm not sure I'm following what's the analogy to restricted Boltzmann machines, because they are unsupervised learning models, and here again it's okay. So let's say actually, I think I can make a connection, and I think it's an interesting question. So let's say that we are in the teacher-student scenario where we have a restricted Boltzmann machine of a certain number of hidden units that is generating data. And we would like to know whether it's helpful to try to learn this data back in an unsupervised fashion with this restricted Boltzmann machine that have more hidden units. So that's a good question, but that's something that I don't really have intuition of, because it's quite different, the objective of maximizing the likelihood of observing the data as you would use in the unsupervised learning, compared to the one that you have here, where it's most probably a classification in a supervised learning training. So I don't know, but I think it's an interesting question. And otherwise, I think what we have learned from these heuristics is maybe what is making overparameterization so beneficial in modern neural networks. And for example, we've seen that we really need to be learning those two layers, because then we are able to have multiple neurons that will focus on learning the same aspect, the same neuron of the teacher, but that are going to be able to average out the noise, because it's like they are actually working in a committee. It's like an ensembling method, if you want, that is very efficient at canceling the noise in the data to be reliable and to generalize. I hope that.
Yeah. And actually, well, maybe this question is a little bit convolved, and if you think we can talk about this later, but in transfer learning, there are many schemes in which their entire feature structure, like imagine a very big convolutional neural network, all the convolutional layers are frozen, so to speak, so they are not being trained, and then there's the final layer which is being trained. Do you think this scheme would resemble the part of what you've shown, in which there's only one single layer that is being trained, and then useless parameters there could go to 0, for instance?
Yes, so exactly. I mean, you're totally right. That's we can say that those analyses where the feature maps are learned and we are only learning some output weights are relevant, because that's, for example, what people are doing a lot in transfer learning. Now, going even further, I know of at least one paper where some colleagues have specifically focused on putting up a scenario where the task was transfer learning and trying to analyze what's going on in this case. And I'll be happy to send you the reference. Maybe I can post it on Discord after the talk, if you're interested.
Okay, yeah, thank you very much.
I have a question about basically how difficult is it to extend the method you use with the replica trick to study deeper models?
So right now, the bottleneck is not really going deeper, in the sense that, for example, if you take those committee machines, we could add layers. But the issue is that actually what we are only learning is going to be, we are only going to have networks that have an infinite number of inputs, but a finite number of hidden layers. And as far as I'm concerned, I'm unsatisfied with this setting. And what we would like to be able to do is to have networks that, okay, we will have to take high dimensional limits, but we would like to have hidden neuron networks, hidden layers that are also going to scale to be infinitely wide if we have inputs that are infinitely wide. And I would argue that this is something that would be closer to what we are seeing in modern practice of deep neural networks, for example. And this is something that, so for now, we can do random feature model where we are actually not learning the first layer, and but we have every layer that is going to infinity. But what is really for now a bottleneck that we haven't, that we are currently unable to solve, although it's very interesting, and I mean, I'm happy to discuss with whoever might have ideas about it. It's to really have extensive layers that are learned. I mean, to have 2 extensive layer learned is something that we, for now, cannot handle with those methods.
A quick follow-up is, can you study convolutional layers, for example?
So thanks for the question, which is a very natural follow-up indeed. No, for the moment, we cannot study convolutions. So if you want, with this, we are relying on some, as I was saying, randomness and concentration effects that are taking place easily in those fully connected networks that will end up have sums of more or less uncorrelated variables that will end up being Gaussian, or if you want more, this is the type of simplifications that is taking place. And with the convolutional filters that are the same throughout the images, those have correlations we are currently also not able to understand.
Okay, thanks. It's a very interesting.
But maybe, yeah, maybe if I want to follow up, it's also a case that I think there must be a way of formulating a minimal example, a minimal convolutional layer example that we might be able to treat, but yeah, it hasn't been done, and it would be very interesting to be done. And maybe as again another follow-up, I must say that all of these are very legitimate questions, but what's really impressive is that we already don't understand how a fully connected deep neural network is doing as well as it's doing. So it's a bit jumping ahead than to be trying to solve convolutional networks in terms of what theory is available nowadays.
Okay, I don't see any more questions. No? Okay, let's thank Marylou again for his very interesting talk.
Thank you very much again for the invitation, and thank you to all the students for the great questions and good interactions.
Okay, Anya, it's on you.
Okay, thanks, Marylou, as well. Okay, so now we have a break. We can take full half an hour and maybe even a little bit more, because then we start with flash talks and the poster session. Regarding flash talks, we have just 2 out of 27 planned. I don't know how it happened at all. So maybe some people will also take advantage of a live flash talks, and they will just give you the